And these stoichiometric coefficients that I've really been forcing you guys over and over and over to produce tell you about a lot of things. Like if I went backwards in this reaction, it would tell you that it takes 2 hydrogen molecules to react with every 1 oxygen molecule. And I should have, for every H2 that's produced, I should expect half of a O2 that's produced. So this allows you to create conversion factors between one kind of molecule and the other that gets reacted one way or the other. Fancy words, but it's really simple concepts. So here we go, recipes. H2O molecules, if you have them convert into H2 and O2, it does exactly what I said. For example, for every H2 molecule that you consume, there's half an O2 molecule that gets consumed. Or for every 2 H2s that are consumed, there's 1 O2 that gets consumed. And we're going to start really hitting this next week a lot. This is reiterating that these coefficients mean a lot. So they mean equivalence. They mean molecule to molecule. Like for every 1 molecule of CO that gets reacted, it takes 2 H2s to get reacted. It means moles. Like for every mole of CO that gets reacted, it takes 2 moles of H2 to get reacted to form 1 mole of this product. So when we balance it, we've covered that before. Here's the interesting thing. We can start thinking about how much of each ingredient you need to add to produce an amount of a product, or of a, I guess, finished dish, to be good with the metaphor. So from this reaction, I can say that it takes 1 mole of P4 for every 6 moles of cobalt. So if I wanted to know exactly how much P4 it takes to react with 0.275 moles of cobalt, I would multiply it by this conversion factor. So you could also ask how much product will be formed from a given amount of a precursor. So you could ask how many moles of product would be formed if we started with 0.275 moles of cobalt. What you do is you'd look at the reaction that we've balanced. It has to be balanced for this to work. And you'd say, OK, for every 6 moles of cobalt, there are 2 moles of the product that are formed. So that means I'll multiply it by a ratio of 2 to 6 to get that number. So this allows me to do kind of a unit conversion from products to reactants, from reactants to products. There is kind of an obnoxious thing here. Because we're scrambling molecules around, we can't just go from grams to grams. We have to, almost always, if you're given a mass and they want you to figure out using a recipe or some other kind of amount, like if they give you a pressure or a volume and they ask you to figure out how much products are going to be formed from that, you need to convert those amounts that are not number amounts, not moles or not numbers of atoms. You need to convert them into numbers of atoms or moles. So those balanced equations we had show us moles to moles. They don't show us grams to grams. So we'd have to convert grams to moles and then use the equation to tell us how many moles of the product we're going to form. And this is the flow chart for that. It's probably better to use an example. So you have carbon sulfide and oxygen. What is the mass of product that forms? When they say excess O2, what they mean is the limiting reagent is carbon sulfide. So every carbon sulfide is going to react. There's going to be some oxygen left over. We don't even care about it. What's going to determine the products is how much of this we have. So we need to convert this into moles. So we're going to use the molecular mass. So here's the molecular mass. We're doing the reciprocal of it. So instead of saying grams to moles, we're going moles to grams. And that'll convert it into moles. And then from moles, we'll have moles CS2 left over. We need to figure out how many moles of a product are formed based on 1 mole of CS2. So for CO2, that's a 1-to-1 ratio. There's 1 CO2 that's formed for every CS2. So we're going to use that conversion factor. And then that leaves us, like at this point, we've canceled grams, we've canceled moles CS2, and we just have moles of CO2 left. At this point, because the question asked us for grams of CO2, it asked us for mass, we're going to have to multiply it by the molecular mass of CO2. So there you go. Haha. And if you multiply across the top, and you multiply across the bottom, and you divide, you'll get that many grams of CO2. You can do the same process for moles of SO2, but the trick here is that in this case, there are 2 moles of SO2 that are formed for every mole of CS2 that's reacted. So that's different. Do you see how there's 2 moles of SO2 for this conversion factor versus 1 mole of CS2? So that helps. That's necessary. And we got that from the balanced chemical equation. So believe it or not, there is some logic to the progression of the course, and you need to know how to balance equations to be able to do this. So overall, the process is the same. We are starting with the mass. We're converting it to moles. We had moles of reactants. They ask us for moles of product. So we find how the chemical reaction converts apparently 1 mole of CS2 to 2 moles of SO2. And so we have that conversion factor here. That would give us, instead of gram CS2, that cancels. And also moles CS2 cancels, so we have moles SO2 left. And then we multiply finally by the formula mass of SO2, and that'll give us grams SO2. But a limiting reagent is entirely consumed when a reaction goes to completion. So, for example, when I burn something, like a piece of trash, there is a lot of oxygen out there to burn. So there is oxygen in excess, and there is whatever I'm burning. That's the limiting reagent. That'll determine how much CO2 and how much water I produce. So the excess reagent is plentiful, and it is not all consumed in the reaction. There's still, thankfully, more oxygen left after I have burned stuff. What we need to figure out with limiting reagent is which one gets used up first. So I'll run out of stuff to burn long before I run out of oxygen. But it's not always that simple. So imagine this recipe, right? We have 1.5 cups of hot water to 2 tablespoons of cocoa powder in a mug to give 1 hot cocoa drink. How many hot cocoa drinks can you make if you have 9 cups of hot water, 20 tablespoons of cocoa powder, and 8 mugs available? This is tough. I need to write this out as a chemical reaction. Okay, so it's 1.5 water plus, look, it's not real chemistry, right? Plus 2 cocoa plus mug 1 drink. Okay. And they give us 9 cups of hot water, 20 tablespoons of cocoa powder, and 8 mugs. So how many times over can we do this reaction if they give us 9? Yeah, so I just divide 9 by 1.5, and that tells me how many times I could do this reaction over and over again. How many times could I do reactions if I just, like, if I had infinite everything else but only 20? 10. And then 8 divided by 1 is just 8. Okay. So bottom line here is I have enough water to go 6 times. I have enough cocoa powder to go 10 times, and I have enough mugs to go 8 times. So I can only go 6 times. I can only go as much as the limiting reagent. So 1 drink, so it's going to end up being 6 drinks. So you can make 6 drinks based on this, right? Because you have enough water to make 6 drinks, and everything else you have more than enough to make 6, so you're good. 6 drinks. Notice that we had, in terms of numbers, we had more water than we had mugs, but the mugs were not the limiting factor here. The water was. Does that make sense? So we need to compare what's going on in the balanced chemical reaction to what's given for moles. Not just look at number of moles and say, this is the smallest number of moles, therefore that's the limiting reagent. No. It's the number of times the moles given are the number of times they are the moles in the balanced chemical reaction. So divide what you're given by what the recipe calls for, and that's how many times you can do the recipe, right? Does this concept make sense? It should not scare you in any way. I mean, like, this is cooking. I mean, literally, this is cooking. It's just like we have a way of writing it down that's very strict, and the periodic formula, the periodic table should now start to be your friend a little bit, right? You know how much things weigh.